Alright guys, we're looking at our summer 2017 paper 4.1 from 0654. This one, it's kind of gone off the rails a little bit with their numbering. Notice we're on question 2 this time, first time I've seen that. Okay, and actually this first question that you're doing is not to do with our syllabus, don't need to worry about that. It's a question all about specific heat capacity. As soon as you see those words in your past papers, specific heat capacity, you can feel free to ignore the question. However, there's bits of it you can do. Okay, so just because you can't do A1 here, alright, we've not learned this equation, Q equal MC delta T. If you're interested, do it. Okay, have a look at my work, pause the video now. Okay, if you want to get cracking on, we can go on to A2, alright, which is a question about efficiency. Alright, now in this case efficiency is on our syllabus. We know that efficiency is the ratio of energy, useful energy out to useful energy, to the total energy in, and then multiplied by 100. Now, this is our standard equation. Alright, this is the equation that we've learned. However, I'm going to use a slightly different one. The one I'm going to use here is that efficiency is the ratio of the useful power out to the total power in, and then multiplied by 100. Now, why am I allowed to do that? Well, you should be able to see that energy is just power times time. All right, so I could replace energy out by power out times time, energy in by power in times time, and then time's going to cancel. So there are two versions of this equation. One of them the ratio of energies, and one of them the ratio of powers. Obviously multiplying by 100. Okay, in this case, we know the power. We know 300 joules of energy each second. That's why it's a power. Okay, we know 2,600 joules each second. So therefore, we're doing 2,600 divided by 3,000, multiplied by 100. Smash it in your calculator, you get 86.66%. Remember, we always want 3 significant figures, so why not do that? Okay, 86.7%. That means my kettle is quite efficient, alright? 86.7% is a very efficient process. Why is that efficient? Well, let's think about it. The kettle, its job is to heat. Usually, one of the ways that we lose energy is heat. Okay, so if you're heating things, if your job is to heat, it's very likely you're going to actually be quite efficient. Similarly, for heaters in radiators, for example, their sole job is to heat. They basically are 100% efficient, maybe not 100, 98, 99% efficient, because that's their job, they heat. Okay, remember in other systems, I'm thinking for example of wheels on a car might rub, might make noise and also heat up. They'll be losing that energy. It's energy we don't want to have. Okay, let's look now at our question about the kettle. Switched on, water reaches boiling point. Okay, it starts to boil and the kettle remains switched on. Explain in terms of molecules what happens. So again, what that really means is use the word molecules in their answer. So I've gone straight in and circled my word molecules there. The thermal energy is used to change the state of the water. And what that means is it is used to separate the molecules into the gas state. Now that is an answer that we could give according to our syllabus. If you wanted to build on it and give an answer which is a bit more including real science, as it were, we would call that the latent heat of vaporization. Okay, there's two latent heats: latent heat of vaporization, latent heat of fusion. All right, in our course we don't need to worry about them. However, that's the name we would give to them in a more official and academic environment. So that's our all for question 2. Nice easy start, I think.